Hello and welcome to our presentation on anti-biofilm nanoparticles by Kate Hoagland, Nathan Leiblin, and Zach Wilson.
So the types of nanoparticles used in our article were polymer, lipid, and polymer-lipid hybrid nanoparticles. And throughout the article, it mentions many different types, like different compositions. There's a couple tables, but there were too many to list on the slide. But the branch that they fall under is polymer, lipid, and polymer-lipid hybrids. All of the nanoparticles that they showed in the article from the pictures, they were all circular, and the sizes for the lipid nanoparticles was 0.055 micrometers to zero 0.9 micrometers, and the size of the polymer in lipid polymer hybrid nanoparticles was 0.02 micrometers and 0.42 micrometers. As you can see in this picture right here, this is basically showing a polymer nanoparticle breaking down a piece of bacteria. So the nanoparticles are in green and the bacteria is in red. And the whole point behind why there's studies on the use of nanoparticles is because it decreases the bacteria's resistance to antibiotics. The application of these nanoparticles. So what I was talking about before was how they can be utilized to treat biofilms. So biofilms it's like a big cluster of bacteria that's super hard to treat, and antibiotics can sometimes not be effective depending on how strong they are. So the idea behind it is that the nanoparticles go and kind of break up the biofilm and allow the antibiotics to treat it more effectively. The reason that this is important to society and researchers is that if we can do this and make the antibiotics work more efficiently, then there won't be as much of a need for them. So overall, the cost of treatment will go down, and that'll allow more people to actually be able to get treatment. So there's a big reason why people are invested in this right now.
Okay, so what exactly did the nanoparticles do? In the anti-biofilm usage of nanoparticles are used to contain antimicrobial agents and deliver them to biofilms in order to destroy them, which are usually otherwise untreatable. Additionally, after being coated with a layer of lipids, a good aerosolization quality of the nanoparticles is ensured. Additionally, nanoparticles' ability to precisely find biofilms allow those who take the medicine to be able to take less. This minimization of the dosage can also minimize the side effects present. Additionally, the biofilms have the ability of a triggered release. Due to the nature of the nanoparticle, it can react to any number of signals, such as electromagnetic radiation, ultrasound, and heat, and release its package only once it receives that signal. Additionally, nanoparticles' ability to penetrate biofilms is the main focus, as not many substances can. And here on this bottom picture, we kind of see what exactly the nanoparticles are doing. We see this blue circle, which are the nanoparticles. And those little black circles inside that big blue circle is the carried package, the medicine that will be delivered to the biofilms. Okay.
All right. How does this improve upon the current technology for this application? Well, to counteract the biofilm's resistance to normal antibiotics to the immune system, specific drug delivery by lipid or polymer nanoparticles has increased efficiency when targeting these bacteria. Using nanoparticles allows, as Zach said, a triggered release of the antimicrobial agent to ensure it gets to the biofilm before it can be avoided by the bacteria, as older methods have seen. The reason lipid nanoparticles are able to deliver the drug more effectively is due to its phospholipid layers it coats around the drug, allowing it to sneak into the bacteria before the organisms can realize what it is and get away from it. As for fusogenic liposomes, their biggest advantage involves the fluidity of its membrane, giving it the ability to deliver the drug directly to the cells as it fuses with the phospholipid membranes. Those are our references, and thanks for watching our literature project presentation.